How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 5.1 and 2 problems, nature of energy and the first law. So let's start with number 1. It says the internal energy of a system, blank. All right, so we got some options. We're trying to fill in the blank. So the internal energy of a system is the sum of the kinetic energy of all of its parts? No. Just the kinetic energy? I don't think so. Is the total of the potential and kinetic energies from all of its components? Could be. It sounds pretty good. Potential, kinetic, that's really all the kinds of energies. C is the sum of the vibrational, rotational, and translational energy of all its components. All these are kinetic kinds of energy, so it's not talking about any potential, so it's definitely not C. D is the sum of the energies of the nuclei of the atoms of all the molecules. It's definitely not that. And E, none of the above. So best answer is B. All right, 2. Which of the following conditions will always result in an increase of the internal energy of a system? With these kind of problems, I usually draw a box, and I call this the system. And then everything else is surroundings. So generally when we're talking about this kind of thing, we're talking about heat, which we usually use Q to talk about, and work as a W. And if we're talking about increasing the internal energy of the system, well, the heat must be going into the system and the work must be going into the system. So the way that we see that, well, it's absorbing heat and it's getting work done to it. It's not doing work, it's having work done to it. So that's what we're looking for. And best answer would be D. Heat is absorbed by the system and it has work done on it by the surroundings. Whereas heat is lost, that's decreasing the internal energy. It won't increase it necessarily, right? Heat is absorbed by the system, so that's good. And it does work. That's not good. So that won't always increase the internal energy. Heat is lost. That's right off the bat bad. It's losing energy and work is done on the system. Well, that's a good thing, but if more heat is lost than done on the system, then overall it's a decrease in energy. So choice D. 3. At what velocity in meters per second must a 20.0 gram object be moving in order to possess a kinetic energy of 1.00 joules? So we got to go, all right, well, what is the formula for kinetic energy? And it's going to equal 1/2 mv squared. So that's the velocity in meters per second, and that's the mass, which has to be in kilograms. So they give me grams, I have to convert that to kilograms. And they're telling me what the kinetic energy is. We're trying to solve for the velocity. So let me rearrange it. I got to times each side by 2, so I get 2 times the kinetic energy. That gets rid of this half, and then divide it by the mass. And then that's going to equal v squared. So I got to take the square root of that, and that gives me velocity. So now I just plug and chug. I'm going to have to do, all right, the square root of 2 times 1.00 joules divided by 20.0 grams in kilograms. It's 0.0200 kilograms. So when I do all that, I get a velocity equal to 0.2, and the units on that are going to be meters per second. That's how you do that problem. 4. How much energy does a 100-watt electric incandescent light bulb consume if left on for 24 hours? You forgot to turn the bulb off, it was on all day. How much energy did it use? Well, first thing that you need to consider is, well, what exactly is a watt? 1 watt is 1 joule per second. So it's measuring like how quickly energy is being used. So if I had a 100-watt light bulb, that's 100 joules for every second being used. And it's going, all right, for 24 hours. Well, let's see. They want joules, so that's fine. I got to get rid of the seconds thing. So I got to times it by, 60 seconds in a minute. And then I got to go, all right, well, let me times that by 60 minutes in 1 hour. And then let me times it by 24 hours and check what happens to the units. Seconds cancel out, minutes cancel out, hours cancel out. I'm left with just joules. And when I plug and chug that, I end up with 8640000 joules. So quite a bit of energy when you're talking about joules being used if you leave a light bulb. Turn the light bulbs off. 5. Which is or are state functions? Well, let's see. Work, which is W, depends on how it went. Remember, state functions depend on just its state of being and not how it got there. So the work done depends on, did it go directly there or did it take a roundabout way to get to there eventually? The work, not a state function. Heat absolutely is a state function. It just depends on, where it is. How much heat does it have inside of it? Or, enthalpy, I should say. It's because heat isn't. But enthalpy is. All right, Q also not a state function. So the only state function here is enthalpy. 6. What is the delta E of a system that absorbs 24.4 joules of heat and does 6.2 joules of work on the surroundings? So again, I draw a box and I go, that's my system. If it's absorbing heat, well, that's heat going into the system. So that's plus a 24.4 joules. And it does work, so it's losing that energy to the surroundings. So it loses 6.2 joules. So I go, what's the overall change? Well, it'd be, it added 24.4 joules, but it lost 6.2 joules from doing work. And when I plug that in and get an answer, it's 18.2 joules, and it's a positive change. So that is my change in energy for the system. 7. What is the change in the internal energy of a system that absorbs, so again, this is absorbing heat, and does that much work on the surroundings? So again, draw my box, label it the system, and it's absorbing heat, so the heat's going into the system. So it's a positive value of 4,200 joules being put into the system. And again, it does work on the surroundings. So it's losing that energy. So it's going to be losing 8,954 joules. So if you want the change in energy overall, you go, all right, well, what was my Q? My Q went up 4,200 joules, but my work, my W, lost 8,954 joules. So overall, what is my change in energy? Negative 4,754 joules. Right. So for these ones, always just draw a box, draw it out. It helps, okay? Frees up space in your brain. Your brain's trying to picture something in your head that's going on. If you draw it down, it can now free up extra space to start thinking about other things. All right, so I hope you found that helpful. I'll see you in class. Okay, bye.